You're listening to the Common Descent Podcast.
Hello, David.
Hello, Will.
And hello, listeners. Welcome to episode 81 of the Common Descent Podcast.
Welcome back.
Yeah, today we are discussing Metamorphosis.
One episode, Gregor Samsa woke up and found himself the topic of Common Descent Podcast.
Too good.
For all you literature fans out there. I'm excited to talk about Metamorphosis because I don't actually know a ton about it.
I didn't either, and I wouldn't say that I do either now. But it's a really interesting topic for a couple of reasons, one of which being because it is so diverse. Mm-hmm. There are so many different groups that do it, and so many different versions of an animal transitioning from one state to another, and our fossil understanding of it is interesting and odd.
Right, so we're talking caterpillar to butterfly, tadpole to frog.
All of those classic examples of something that is born in one life stage and then notably changes to a later life stage. We'll go over the definitions because they are not singular, but it is a very odd phenomena in life that is surprisingly common and has taken many different forms, as well as had a huge impact on the evolution of life. So we will go into what it is, what are the varieties of it, not every single one, because even within a single group of insects, it can be very diverse.
Yes, this is but one episode.
Yes. But we'll go over what are some of the examples of the organisms that metamorphose, what is some of our fossil understanding, and how/why do we think it evolved? Because that's a big question of, okay, but why add 3 steps to growing up?
Yeah, I'm curious too.
Yeah. So we'll go over that. This episode is also cool because it was requested.
Oh.
Our requesters include Jonathan and 2 of our patrons, Tom and Sycorax.
Thanks for requesting.
Yeah, I was very excited when you did, so thank you all.
This is one that I don't think would have been on our original list, even if we had... This is one that was definitely not on our original idea list back in the beginning, and given time, I don't know that we would have thought of it.
Yeah, I'm not sure. Because one of the things, when we first saw it came up, we both went, oh, I don't know how we would... And then as I kept thinking about it, and as we kept discussing it, I got really excited, so I put it on my list to force myself to do it.
And here it is.
But before we get started, as usual, let's get out of the way some of our announcements. Today we have very few. Our biggest one is the one we have had every episode for a while now, in that when we get new people on our Patreon, because we have one of those.
We sure do.
And if those people are at a certain level, like these people are, we shout their name out. And today we have Susan to welcome.
Thanks for joining us on the Patreon, Susan.
Yeah, thank you.
Everyone else, Susan already knows this, but patrons on our Patreon get all sorts of goodies.
Absolutely.
Bonus content, bonus audio, cool stuff to listen to, so if you're not on there, check it out.
Yes. And our only other announcement is about the announcement we made last time, in that we are still on Instagram.
Yeah, check us out on the gram.
So go see what we're posting. We're trying to post regularly.
On our Insta. Look how hip and cool we are.
All right, moving on quickly.
We got to get a TikTok. Or if you're listening to this in 6 months, whatever the new thing is, we got to get one of those.
Vine 2.0. Well, before we get on to our discussion, and now that we've finished announcements, we have entered the territory of the news.
News time.
We like to start every episode with a bit of news from recent discoveries, recent researches in the scientific fields of paleontology and evolution and the like. Keep us up to date, and to keep you up to date, and to keep us up to date today is going to start with David here.
Oh, that's me. Well, we are a paleontology podcast.
Yes.
And we like to explore topics that are diverse and all different types of research by all different types of researchers. But today, I'm going to talk about tyrannosaurs.
Hey, I like those as a paleontologist.
They're pretty cool. This first bit of research is about a new species of tyrannosaur from Canada.
Cool.
This is research by Jared Voris et al. In the journal Cretaceous Research, and indeed it is about research from the Cretaceous. And we'll link to an article in Live Science by Laura Gegel. Tyrannosaurs are a group of dinosaurs that lived in North America during the late Cretaceous, also other places, but famously in North America in the latest parts of the Cretaceous, including, of course, the famous Tyrannosaurus rex, and then a bunch of others like Albertosaurus, Gorgosaurus, Daspletosaurus, and so on. In this new research, researchers report 2 new partial skulls, skull and jaws, of a different type of tyrannosaur from Alberta in Canada during the mid-Campanian around 79 to 80 million years ago. Based on features of these skulls, they have identified it as a new genus and species, which they have called Thanatothyristes degrutorum.
Wow.
Thanatothyristes means reaper of death, because it's a tyrannosaur, and this is what dinosaur researchers do.
Yep.
Degrutorum is named after the discoverers of the fossils, or at least the first fossils, John and Sandra de Groot, who discovered it a decade ago, back in 2010. Both specimens were found in the Foremost Formation, a geological formation in Alberta, which was also home to ceratopsians like Xenoceratops, and pachycephalosaurs like Colepiocephali, among other stuff. Several things are very interesting about this new tyrannosaur. For one, it is the oldest tyrannosaur on record in northern North America. So northern North America meaning Canada and the northern United States.
Mm-hmm.
It's the oldest described tyrannosaur on record from that whole section of the continent, and it's the first new tyrannosaur discovered in Canada in about 50 years.
Wow.
So it's a cool record breaker in a couple of ways. It is a big animal, as you might expect. The skulls are about 80 centimeters long at estimated full length, so just under 3 feet. And the full animal is estimated based on other tyrannosaurs to have probably been about 8 meters or 25 feet long, which for a tyrannosaur ain't bad.
Yeah.
Notably, it has this unique set of ridges on the skull that run from the eyes down the snout. It's one of the unique features of the animal that it has this cool, like, ornamentation on the skull, which is cool because other tyrannosaurs had weird skull stuff going on, like sort of little horn, not horns like Carnotaurus, but bumps and crests and stuff.
Yeah, the eyebrow ridge type things and stuff like that.
Exactly.
Cool.
Based on the shape of the skull, they suspect that it is a close relative of Daspletosaurus, which is another North American tyrannosaur. And indeed, they put the 2 of them in a new clade, the Despletosaurini.
Oh.
Which led them to what I think is the most interesting result for me of this study, which is that they point out that as we are discovering more tyrannosaurs, the old idea of it just being one family group with a bunch of different species in it, or a bunch of different genera, single branches on a tree, seems to not quite be the case. They suggest instead that they were multiple groups across this tree, and each group had a couple of different members.
Okay.
So this new species and Daspletosaurus were in their little group, and you had these minor groups of tyrannosaurs spread around North America, which ties into their suggestion of a phenomenon called provincialism, which is to say that different tyrannosaurs were inhabiting different places.
Yeah, providences.
So that in different territories, in different areas of the continent, you'd have different types of tyrannosaurs with different body shapes, probably living slightly differently with different hunting styles or different lifestyles in some way or another. So that if you travel over here at this time period, you're going to see the Daspletosaur group, and if you travel over here, you'll see something else.
Cool. I like that.
Which is a pretty cool... and it's sort of like if you imagine in the U.S. today, where you've got brown bears in one part of the country and black bears in another part of the country, and they don't always overlap. They are living different ways largely in different places. I guess polar bears are another really good example to add to that one. Living in a whole other place, not often overlapping with the others, doing their own thing.
Well, and it makes sense, as with bears, from the predatory stance, that if you are large predators, you don't want to be on top of one another.
No.
Because you're probably all looking for at least similar stuff, and especially if you're willing to take carrion, that's going to end with fights when you come to the same carcass.
Right. It's a great way to niche partition.
Exactly.
By just not ever seeing each other.
Yeah. Well, you see a little bit of that in South America with all the caimans, that there are areas where they overlap, but there's also lots of instances where it's like they overlap here, but then this species kind of balloons out this way.
Right.
And this is really where they're more common and the others aren't as common. So that's cool.
Yeah. So a new tyrannosaur with a ridiculous, awesome new name.
With a heavy metal band name.
Some artist out there make a piece of artwork with a bunch of different rocker named dinosaurs in a band together.
Diablosaurus and
Diabloceratops.
Diabloceratops.
Yep. Have fun.
Well, to keep up the awesome levels, I will talk next about chameleons.
Oh, wait, those are pretty cool. Cooler than tyrannosaurs, some might say.
Oh.
I would say that.
I said that. That was me.
That was me. You can quote me on that.
So chameleons are those usually fairly small to medium-ish lizards that most people are familiar with. They're tree climbers. They've got that coiled prehensile tail. They've got that famous launching tongue and those separately aiming eyes and the little alien karate chop hands, if any of you watch the True Facts. They are well known in certain spots of the world, but where they originated has been a little debated. And so this is a bit of updated research on that concept of where we think they came from. This is research by Andrei Cernansky, apologies for pronunciations, et al. In Scientific Reports, and the press release in phys.org is also by Andrei. So chameleons, in the group Chameleonidae, are composed of about 213 species worldwide, and worldwide being Africa, the Middle East, southern India, Sri Lanka, and the Mediterranean. Mostly, though, on Madagascar.
Right.
That is where the hot spot of their diversity and about half of the species are found. So, this has been considered a very likely candidate for the origin of chameleons.
Makes sense.
This is where most of them are, and they're scattered around the surrounding areas, but they're not nearly as common, or successful at least, in those. So, it's been proposed that they originated in Madagascar and then came over to mainland Africa through ocean dispersal. So rafting, riding the water either on debris or with the help of a storm.
Right. More on that kind of thing in episode 40, where we talked all about Madagascar.
But a study back in 2013 came out that disagreed with that initial proposal. They suggested that they more likely originated on Africa and then migrated once again through ocean dispersal to Madagascar.
Right. And then hit it big.
And then did great there. And this was mostly based off genetic material.
Okay.
So, bit of research. The main thing the research was missing to be really convincing was fossil evidence supporting this. They did not have the fossil, a chameleon fossil in the right place and right time to support that they came from Africa originally. This research is about a chameleon skull from Kenya.
Ooh, which, if I remember my maps correctly, is part of mainland Africa.
It is. This skull was from a chameleon genus that is only found in Madagascar today, the Kaluma, and due to the age of the fossil, back to the early Miocene, about 18 million years ago, shows that they originated in Africa. The fossil comes from an island near the coast of mainland Africa and is one of the oldest chameleon skull fossils ever. So it dates back to early periods of the chameleon group and is early enough and new and unique enough to get a new species name.
Cool.
Which is Kaluma benovskii. And so now this supports that past research that they originated on Africa and then migrated to Madagascar. But part of the reason people were questioning of that migration is that the ocean currents don't support it today.
Interesting.
The currents move from Madagascar to Africa, and so it would be very difficult for an animal to raft. But
it'd be difficult for them to raft the other way
yes.
to go. It's much more likely that you would come over from Madagascar to the mainland.
Absolutely. But ocean research of the space between Africa and Madagascar show that in the past it used to flow eastward toward Madagascar and has switched since then. So back in the Eocene and until the early Miocene, the flow would have actually promoted dispersal from Africa. And then after that, it switched backwards to a westward tendency to what we have nowadays. So today it wouldn't be likely for them to disperse from Africa, but when they originated, it would have been much easier.
Very interesting. So we have the oldest chameleon fossil of this group and one of the oldest chameleon fossils, period, over in the mainland. Interesting. That makes me wonder how much... I'll be very interested to see if we continue finding chameleon fossils in Madagascar, if it flip-flops. Like if this stands as now the oldest one and matches up with the ocean currents to support the idea that they started in the mainland and moved over. Very interesting. But let's see what happens as we keep excavating more in Madagascar.
They do point out that it is also supported by other animals, like the eye seems to have also had a similar dispersal from mainland Africa to Madagascar.
Interesting.
Yeah, so it's not the only group that seems to have made this trip this way.
It's always fun to try to figure out ancient paths of dispersal.
Yes.
Especially when you have island situations where the question is, how did you get from here to there? Where did you originate? And then what does that tell us about your early evolution? Because with a group like chameleons, they're such a very specific, unique type of lizard that it would be very interesting to know how they got started. What was the early evolution of chameleons? How did not chameleons become chameleons? And questions like this help us to understand where to look.
Yes,
for the answers to those questions, which is very cool.
Yeah.
Well, that's fun. Hey, go back to episode 4 for island evolution and episode 40 for Madagascar. Well, for my second news, I'm going to go ahead and continue this trend of talking about reptiles the whole time with news about turtles.
Cool.
Not just any cool turtles, the largest turtles.
Nice.
Get ready. This is research by Edwin Cadena et al. In Science Advances, and we'll link to an article in Sci News by Enrico de Lazaro. Some of our listeners may have heard of an extinct turtle called Stupendomys geographicus.
Yeah.
Very famously, a freshwater turtle from the Miocene of South America, so back around 10 million years ago and thereabouts, famous for being enormous.
Huge.
Like a shell longer than me.
Yes. It's a bed-sized turtle.
It is an actual bed-sized turtle. First discovered in the 1970s in Venezuela. It has been found from a number of partial remains. And then there are other sites around northern South America that have other large turtles. And there has been some discussion in the past of how many different large turtles are there? How many of these are Stupendomys? What was the nature and distribution of this enormous turtle? Well, this new piece of research describes several new shells from a variety of locations and the first lower jaw fossils of this taxon, this species of turtle.
That's exciting.
The new fossils come from multiple sites in Venezuela and Colombia, and by comparing them to other fossils in other parts of the continent, these researchers suggest that a bunch of those other large turtle specimens are also Stupendomys geographicus, which, if so, would mean that this animal was in Venezuela, Colombia, Peru, and Brazil, and was just generally common across northern South America. not just across what are today multiple countries, but in rivers and lake deposits.
That's really interesting.
So this widespread freshwater turtle just owning all of these ecosystems.
Being massive all over the place.
Yep. Among their new discoveries is the largest complete fossil shell ever discovered for a turtle, measuring 2.5 meters long, or 8 feet.
Jeez.
The shell. 8 feet long, and the researchers estimate that it would have weighed in total about 1,100 kilograms or 2,500 pounds. That is a turtle the size of a car.
Wow.
Weight-wise, that makes it about twice the size of our largest living turtle, which is the leatherback sea turtle. The other really cool thing that they noticed, now having several different shells to compare, is that not all the shells are the same.
Oh.
Some of them had horns.
It's not what I was expecting you to say.
Some of them had horns. Now, bumps and stuff on shells, we see that in turtles today. Snapping turtles have those sort of ridged shells. There is at least one group of turtles today that has these little horn-like projections on the shell.
Yep.
In Stupendomes, they noticed these horn-like projections, these sort of pokey bits, up at the front and sides of the shell. So 2 in the anterolateral portion of the carapace, which is to say, toward the front of the top of the shell and off to the sides. And they point out, which I thought was very cool, that there are deep grooves that run along these projections on the shell that suggest that they were true horns with a keratin sheath.
Whoa.
So there were scutes that sat over it, which is the way that, like, bison and a lot of big mammals with horns have horns.
That's exciting.
Which is very cool. And taking a step forward, obviously the next question is, well, why would you have horns? Well, that might be partially resolved by the fact that they noticed that the shells with horns tend to be larger than the shells without horns.
Yeah.
Which suggests this might be sexual dimorphism. That you might be seeing male and female versions of shells.
Which is always exciting.
Because there are turtles today that'll have projections on the shell that will fight each other over mates.
Yeah, jousting tortoises.
Yep, tortoises will do it. So the authors suggest that this may have been these car-sized freshwater turtles that would have, like, poked at each other with their shell horns in fights over territory or mates or whatever.
I literally can't even imagine.
You literally can't even.
Can't even. I actually can't picture what that would look like.
That's a kaiju battle.
Like, is that just two of those going at it in the river would be so noisy and so violent.
Yeah.
That's awesome.
They also made a couple of conclusions about diet. So in the past, Stupendomes, it has been suggested that it may have functioned like a giant snapping turtle, which is a terrifying thought, as any of our listeners who have met snapping turtles can probably attest. But these researchers with these new jaw specimens point out that the turtle's jaw looks like it could also have been good for eating larger, tougher things, like mollusks.
Okay.
It's like shells and stuff. Or fruit.
Yeah.
That it could have... They actually point out that it could have been a major seed disperser. Because it's a megafaunal animal. And one last thing, while we're on the subject of diet, one might wonder, well, what could an 8-foot-long turtle have to worry about? Well, they did find on multiple specimens bite marks and one isolated tooth stuck in a shell because the Miocene of South America was not home to just one giant type of reptile.
Nope.
Will.
This is the home of the biggest caimans that ever lived, Purosaurus.
Yep, and the authors suggest that this tooth and these bite marks look like they came from large crocs, and Stupendomes overlaps with Purosaurus.
Because this is fantastic. Because, like, 8-foot shell is ridiculous, but that's only 2 feet longer than Purusaurus's head.
Yep.
Yep. So if you're a medium-sized Epindemes, yeah, you're meal-sized.
Yep.
Awesome. That's just, it's cool, and the suggestion of another version of that combat is really interesting, because like when tortoises do it, it's a very specific kind of wrestling. So now I would love to see people do some reconstructions of how these spines would have interacted.
Well, I'm sure it'll happen.
Yeah.
I'm sure there are artists working on it right now. I sure hope so.
Very cool.
Yeah, northern South America has apparently long been the place to go for ridiculously large reptiles.
It's the Amazonian region just has been a nice spot to be a big reptile for a very long time.
It's got the largest modern snakes
Mm-hmm.
and the largest fossil snake.
Yep.
Both from northern South America.
It's pretty impressive.
It's a cool place.
We should go there.
Yeah, we'll take a trip.
Well, I think it's high time we talk about dinosaurs again.
Oh, well, it has been a while.
It's been a bit.
It's been a spell.
And so I have a bit of research on some dinosaur eggs and the information they can tell us about dinosaur body temperature.
Well, this is exciting.
It's pretty cool. This is research by Robin Dawson et al. In Science Advances, and Ruth Schuster is the author of the article in Haaretz. So this is not the first time we've mentioned dinosaur body temperature.
No.
And it's not the first news we've done on it, and it very likely won't be the last.
No.
For a while now, the research has been pretty heavily leaning toward dinosaurs had a form of thermoregulation. They could maintain at least a higher body temperature than the environment around them, if not the same way as us or the same temperatures as us, which would be the classically warm-blooded. Though the paper does have a section going over that warm-blooded, cold-blooded are terrible terms, and that there's a lot of in-betweens there. So read the article if you want to see if you want to learn a lot of cool alternatives that animals use to maintain or partially maintain their body temperature. But the idea has been pretty well supported or accepted that, like birds and mammals, dinosaurs could stabilize their body temperature, and this research supports that, but it looked at it in an interesting way. It looked at the eggs of various groups of dinosaurs to see how the chemicals were formed, because they would have formed differently in different temperatures.
Oh, that's fascinating. Because
Yes.
it's a chemical reaction.
Mm-hmm.
And as we remember from chemistry class, chemical reactions happen differently in different temperature environments. So, wow!
Yeah!
So you're studying a thing that was inside.
It's the closest
The
we can
body.
get to a thermometer.
Yeah, it's a thermometer. Wow. Go on.
So they used clumped isotope technique to look at the chemical bonds of the heavy isotopes in the calcium carbonate minerals of the eggshell.
Okay.
Because details about those calcium carbonate molecules will tell them roughly what temperature they formed in.
Okay, so how the different atoms and molecules are linked to each other, those chemical bonds will be different based on different temperature environments.
Yes. They looked at various groups, to be specific, the sauropods, which are the long-necked ones, the theropods, which are the two-legged predatory ones, and the ornithischians, which are your...
Everything else.
Everything else. Stegosaurus is in there. That's the example they used. And I
So
like that.
they hit the big three.
The big three.
Theropods, sauropods, ornithischians.
And they picked eggs from colder places. Because, as they said, if we picked a warm place, then it wouldn't matter. Because if they were just keeping their body at the temperature of the environment and we picked a warm spot, then they're going to be warm.
Right, they're warm regardless
Yes.
of how they're regulating temperature.
So they went to a place that should have been colder than we expect they were keeping their body. Because then if the temperatures are higher, it shows that the bodies were maintaining higher temperature.
Right.
So they went to Alberta, Canada, and Romania.
Okay, northern North America and northern Europe.
Yes. And they got from there a Troodon and Myosaurus from Alberta, which gets your theropod and your ornithischian. and then a sauropod from a titanosaur, dwarf titanosaur from Romania.
Ooh, the one from the island.
Yes.
That's cool.
So, with these eggs, they did their analysis, and what it came out to is that the internal temperatures would have been similar to birds, between 35 and 40 degrees Celsius.
Ooh.
I forgot to look at what the Fahrenheit calculation is.
Sorry, our fellow Americans.
You will have to do the calculations for yourself. But came out there, which would have been fairly warm. So that's like birds today, keeping at a moderate temperature. Now, they did caveat themselves to point out that at the time that these dinosaurs would have been alive, both Alberta and Romania would have been in what we would classify as subtropical regions because of their positioning and the temperature at the time.
Right. So not cold.
So not cold, but they both were colder than those temperatures. Alberta would have been like 25 to 28 degrees Celsius, and I think Romania was around that temperature as well.
So the internet informs me, for our local listeners, that 35 to 40 degrees Celsius is between 95 and 105 degrees Fahrenheit. So if that sounds familiar, that's because that's what your body temperature is.
Yes.
At least I hope that's what your body temperature is.
Or you should be listening to this in a hospital. So yeah, the eggs support endothermic, a warm-blooded temperature for these egg-laying dinosaurs.
That's interesting because I've read, and we've talked about this kind of research on other episodes, and I know that there's been research done on, I think, bones and maybe teeth that have looked for similar chemical information. And I remember reading a bunch of others that found very similar results, that it is very bird-like or intermediate between birds and something like crocodilians or lizards that you'd have today. So it's a fun conclusion because this warm-bodied dinosaur hypothesis is now being supported by many different lines of evidence in many different clever ways.
Well, and because now we're very quickly getting to a point where the question isn't whether they maintain temperature, it's how and what degrees.
Right.
Like, it's pretty well supported. No, they were definitely warm. But how warm, and how were they doing it?
How warm were they, and how were they warm?
Yes.
Yeah.
Which is cool.
I'd also be very curious to know, as this develops further, if we find differences between different groups of dinosaurs. Mm-hmm. Because that's true in mammals today.
There are mammals that don't maintain very high heats.
So I'd be fascinated to know if, sauropods and dromaeosaurs had similar body temperatures, and if they did, are they maintaining it the same way? Are dromaeosaurs being little and bird-like, and sauropods are just being enormous furnaces?
Yes.
It's like, because dinosaurs, the more we study dinosaurs, the more we see that there is this incredible variety. And I suspect that the more we learn, the more this will prove to be another thing on that list.
Yes. One thing that this research also suggests about thermoregulation among dinosaurs is that since it was found to be similar in all three of these groups, it suggests that it's very ancestral.
Interesting.
That this probably goes back to the earliest lineages of dinosaurs because it was so consistent among these three groups.
Yeah. Wouldn't surprise me.
Yeah.
The earliest dinosaurs, episode 21, are inferred to have been highly active, bipedal, running around, all the things that we associate with warm-bodied animals today.
Absolutely.
Very cool.
And with that, we can wrap up news.
With that, we can watch the news section transform spontaneously into the main discussion.
And we can start talking about metamorphosis.
I'm here for you.
Yeah, with some excellent transitions.
I segue for a living.
So metamorphosis is a concept that most people are familiar with because we learn about it in first grade.
It's very famous.
Yes. Like the classic,
biologically and metaphorically.
Yes, exactly. It is something that is a given for certain groups of life. Butterflies or caterpillars metamorphosize into butterflies. Tadpoles metamorphosize into frogs. But the process that they go through is very weird and not as well understood as its commonplace awareness would make it seem. It's a concept that has been very misunderstood in the past, but also has lots of variety. Like, just tons of different ways to do it. And the different ways are all handled differently depending on which group you're looking at. And so, what is metamorphosis? The basic of it is a change from one body form to another. One stage of life to another. And the body form, though, is the important part, because stages of life can be kind of arbitrary, when we talk about juveniles, young adults, adults.
Right.
With us, okay, well, other than puberty, what is a young adult versus an adult? It's whether you can drive. Like, there's not a clear definition because our body form hasn't changed.
Right. We talked in episode 33 all about ontogeny.
Yes.
Which is growth and development over time, which we do.
Yes.
But we don't metamorphose.
So the real key here is that it is a life cycle organized into morphologically, physically and behaviorally distinct phases.
Right.
You could not point at a baby butterfly and be like, yes, look at all the ways it's the same as the adult. Because one is a wriggly fat thing and the other one has wings.
Right. One crawls on trees and eats leaves. The other one flies around and collects nectar.
Mm-hmm.
Like, fundamentally different body shapes and lifestyles.
And the metamorphosis is an abrupt transition between those. It is not that slowly it grows up into it. That there is a definite shift.
Right. The screen changes and a little dialogue box pops up that says, "What caterpillar is metamorphosing?"
Exactly. Typically, what this means is an animal that is going to go through metamorphosis starts as a larva. Not always, but usually the first stage is known as a larva. And this is the juvenile state. And then after metamorphosis, it transitions into a young adult state. It may still do growing. It may not be fully mature yet, but it is now in the body form of the adult. And from there on, it will do whatever it's going to do as an adult.
Right. Tadpole versus frog, caterpillar versus butterfly.
A lot of times, these include behavioral shifts. I was eating leaves, now I'm drinking nectar. I was scraping algae as a tadpole, now I'm eating bugs. It also can include behavioral shifts. Here I was eating, now I'm mating.
Right.
There's a lot of animals where the different parts have very distinct roles. And this is by no means the rule. For everything we say, there's going to be exceptions. And we'll hit on a number of those, but we're going to miss some. And I'm sure there are going to be people out there that's like, you said this, and there's this one that doesn't. Yeah, I didn't know, or I do know. It depends on.
We have said the word insects in this episode, which means by default that we will be leaving a lot out.
And insects are going to be a big part because most of the things when you look up metamorphosis are going to be talking about insects, because insects, most of them do it, and they also include almost all the versions of metamorphosis that there are to have.
I assume they're also easier to study.
And they're the ones famous for it.
Yeah.
Like, it's also much more notable with them. Insects are what a lot of the terminology is based on. It's what a lot of the articles about it are going to be based on. So, for instance, there are typically 3 categories of metamorphosis. Ametaboly, which is no metamorphosis. You are born as a little version of the adult and you grow up. I didn't see anything that said that technically is what we do. Because it's never used on us.
Right, I was going to say, I guess you use that term to distinguish different groups of insects or whatever, whereas there's no reason to ever talk about metamorphosis for mammals.
Exactly. Then you have partial or incomplete metamorphosis, which is hemimetaboly, and that is the young looks mostly like the adult or behaves similarly, but it at some point molts, or it does have a shift into a mature and usually the sexually mature adult. And so there are two distinct phases, but the first one is not worlds apart. It's just a weirder version or a younger, less developed version.
It's like the end of Splice.
Yes.
You just gained a couple extra parts,
yeah.
and now you're ready to do a few new things.
But mostly, I can tell it was you. Then you have complete metamorphosis, holometaboly, which is you start as a completely unrecognizable larva. Then you go through a pupal phase, which is inactive point where you are shifting from larval to adult form.
Right. Pupil, not like in your eye, but like pupa.
Yeah.
Like
P-U-P-A.
The cocoon that a caterpillar encases itself within.
And we'll go over those terms because there's a few different terms that surround that, and they can get really confusing. But these three are the main groups of metamorphosis, and they're all typically referring to insects when they're being used. Like, I didn't find anything that used these terms to refer to anurin, frog, and salamander metamorphosis or fish. These categories are, like, the terms that surround metamorphosis usually come from studying insects. So let's talk about insects. We're going to go through some of the varieties, and we're going to start with insects because they will give us a good idea of what the range is. And insects include all three.
As with so many things, insects did it first.
Yes.
They're like the Simpsons of animals.
Right. So insects, and it's fun because they actually were preceded by crustaceans who also metamorphosize.
Good point.
But insects kind of had to redo it, which we'll go over later. But they do have all three categories, and different groups are broken up into these three categories. There's actually one of the groups that is named for having complete metamorphosis. Your ametabolous insects are the ones that don't really go through any shift, and typically are also considered the more basal or more primitive, usually the more ancient groups like bristletails and silverfish.
Right.
Egg, young, adult. Boom.
And those are also wingless.
Wingless.
Which is also a basal trait in
Yes,
insects.
it is.
So they branched off, they originated before wings became a common thing and before metamorphosis became a common thing, which I'm sure we will discuss may or may not be related to each other.
And that's something that is a key feature in our other two forms of metamorphosis, is that wings do not show up until the final phase.
Right.
You are not born with functional wings until you have metamorphosized, right. And then you're an adult.
You metamorphose into a flying adult.
And so that distinction makes sense with that knowledge. The partial metamorphosis, I'm going to mostly use complete and partial because it's easier than the terms.
Hemimetaboly or hemimetaboly and holometaboly?
Holo, yes.
For those of you keeping track at home.
But the partial, our hemis, are ones that go through a nymph versus a larval phase.
Okay.
So once they hatch, they are a nymph or naiad for a lot of the aquatic ones. And this is a form similar to the adult, but lacking mature sexual organs, lacking wings, and often living in a different area or habitat maybe. Mm-hmm. But sometimes often feeding the same way. So like if they may be predatory from naiad or nymph to adult.
And I know just by the words you're using that my favorite group of insects must be included here.
Absolutely. This is going to include your dragonflies, your cockroaches, and grasshoppers, as well as true bugs. So there's a group that are the true bugs.
The hemipterans?
Yes.
Yeah.
And
the quote-unquote true bugs.
Yeah. And these include like assassin bugs and stuff like that. A lot of the stinging mouth, the
piercing mouth parts. I think aphids might be in that group.
I'm not sure.
Don't quote me on that, listeners. Because there's also the homopterans.
Yeah.
And when I studied insects in the past, I always got the two confused.
These go through a active nymph phase. And like I said, mostly they're very similar. Like if you look at the naiad or the nymph of a dragonfly, it has a dragonfly face.
Yeah.
It's got dragonfly mouth parts. It's even got the right number of legs that are all proportioned basically the same. It's missing wings,
Mm-hmm.
because that's a thing of it. It does have a different hunting strategy. It has that special feeding arm that's under their mouth that launches out to grab food.
Right, because dragonflies are
Because they're the best.
best insects.
Because they're awesome. But they're aquatic. And so they breathe with gills. And naiads and nymphs are typically very active and feeding, and they will molt multiple times. So once again, for your exoskeleton creatures, the hard-skinned creatures, you need to shed your skin, molt, to grow it and get bigger, because your skin is not flexible and easy to manipulate like ours. So they will go through multiple molts, and then the final molt of the nymph stage is where they will shed their skin and reveal an adult body. And so
their final form.
Their final form. It's very Cell. And when they have that final molt, that's when they will reveal fully formed wings, if they're going to have functional wings, and be ready to become a mature, sexually active adult.
So it's like the ending of Splice.
Yes. And it's, I love grasshoppers for the example, because like if you've ever seen a baby grasshopper, they just look like a cricket. Like,
yeah,
they just look like a smaller grasshopper, and then they don't have functioning wings. But they're still eating grass, and they're still hopping. And like
they're checking the check boxes.
It's a grasshopper, but it's just a baby grasshopper. And then at some point it sheds, and the wings are now functional.
Yeah.
What a lot of them will have are wing buds. So you'll see where the wings are going to be, but they're not functional and they're not fully external. And then when that final shed happens, where those were, developing inside those were the functional wings. The famous one, the one that is the most complex and weird, and definitely will get a chunk of our attention, is the complete metamorphosis, the holometabolous insects. These are, as an egg, then you hatch into a larva that is usually wriggly and soft.
Right. Caterpillars, maggots.
Yep. They also have those different terms. Maggots for flies, caterpillars for moths and butterflies, grubs for beetles, and then just larvae for the Hymenoptera.
Slimy yet satisfying.
Slimy yet satisfying. This is going to include beetles, butterflies, flies, and wasps. Most of your insects.
And outside of dragonflies, most of the cool ones.
Yeah. So you are born as a larva. Usually you eat. This is a very active feeding phase. Put on a lot of body mass. Then you pupate. You go into a dormant, non-feeding, typically inactive phase. That is where you transform very quickly your larval body into an adult body in one of the most ridiculously sci-fi aspects in nature. And then you shed that pupa to be an adult. This is where metamorphosis is so clearly distinguishable, because now it is two very distinct body forms, and there is a definite transformation stage.
Right. They're like a transformation sequence.
Yes,
like
exactly.
a Sailor Moon sequence that you have to go through to go from caterpillar to butterfly.
Just a lot less dancing. So, what happens in that pupa is a very interesting and an often researched aspect of this metamorphosis. So first, a pupa is the dormant stage. There are different kinds of pupa for different groups. In butterflies, it is a chrysalis. So butterflies do not have cocoons.
Okay.
The chrysalis is just a special outer form of the skin. They molt into the chrysalis, and it's a hard, basically external skin, inside which they metamorphosize, and then that is also molted, and they split out of that. A cocoon is something you weave. Moths weave cocoons around themselves out of silk, and then they pupate inside the cocoon.
Interesting.
Yeah, cocoons are also used in, like, that term is used when spiders wrap stuff up and stuff.
Right.
So it's a weaving thing, not the pupa itself.
Cool.
And then everyone else just pupates. Like, the pupa of an ant and a beetle look like an ant and a beetle because they are forming into those new skins. So, like, a lot of times if you look in ant nests, you'll see what look like a bunch of white ants curled up and not doing anything. Those are ant larva pupas. That when they split, they will be in the shape of that ant skin. So what happens inside the pupa is ridiculous. The first thing that happens is the larva digests its body.
Buh.
Into goo.
Buh.
literally, if you cut open a pupa at the right time, like if you cut open a chrysalis at the right point, caterpillar soup, as one article called it, would pour out.
Wow.
They liquefy their body, except for a couple of parts called imaginal discs, which are groups of cells that develop during the embryo phase, during the egg, that have the coatings, have the information for all the adult body parts they'll need. The wings, the legs, the eyes, the antenna, the nervous system, whatever it is. And those survive and then use the soup to quickly develop, split their cells and develop into the adult body parts.
Wow.
And this is something that can happen fairly quickly and is a ridiculous amount. One article said the imaginal disc of a fruit fly wing can go from 50 cells to 50,000 during the metamorphosis.
Wow.
So it literally reshapes their body in one big complicated step of their life.
It breaks down the body and then rebuilds it.
Yes.
Wow.
This is Ultron style of updating your body.
That is very sci-fi.
It is. And there are also weird things about it. Like, one research found that potentially a group of moths called the California Sphinx moth could retain memories through that. So they tested some moths, and the way they did it is they would expose them to a smell, and they give them a little shock to make them not like that smell.
Mm-hmm.
And then when they pupated, the adults still didn't like that smell. Now, you had to do it later on. You had to do it right before they went into the pupa phase, because if you did it too soon, the part of the nervous system that would retain that hadn't developed yet. In the caterpillar.
They were too young.
They were too young. So they'd remember it as a caterpillar and then forget it when they became an adult.
Interesting.
So, but there are certain things like that we're still figuring out exactly what all happens and what it means for the life of that insect.
Right. So you're not just a totally different person.
Exactly. Yeah. You're not the new individual.
Right. Oh, that's fascinating.
It's super weird. Now, like I said, crustaceans also do it, but theirs is less dramatic. But they do tend to have a common theme in that their larvae are usually living a very different way.
Right.
So crustaceans, your crabs, your lobsters, your isopods, most of the creepy crawly things in the ocean are typically benthic, meaning they're on the bottom. They're crawling around the seafloor, reefs, rocks, tide pools. But their babies aren't. Their babies are free-floating. Their babies are the majority of plankton.
Right.
The free-floating little organisms, zooplankton, the animal-based plankton that things like filter-feeding fish are surviving off of.
Right. Plankton are at the whims of the currents, whereas pelagic organisms, you are actively swimming.
Yes, so these are organisms being washed around, and there are some that are more pelagic that can move themselves, but most are free-floating. They usually partially resemble their adult form, but with different features more prominent. Like a little baby crab has a tail like a lobster.
Right.
But adult crabs do have the remnants of a tail on their underside. It's part of what makes up the area where eggs are kept for female crabs.
The brood chamber.
Yes. But it's no longer functionally a tail. But as a baby it is, and they're usually see-through. And the reason for this is dispersal. Have your babies, spread them across the ocean. So a lot of times they're in this form for a long time. And then as you're eating, feeding off free-floating food, and then you molt, you eventually settle down and become a little baby crab.
Yeah.
So still metamorphosis, just without a pupa. So more similar to the grasshoppers kind of way. And then most fish go through metamorphosis.
Yeah, they start as larvae.
They start as a larva. But saying larva fish sounds like a very alien term. And usually you don't hear them called that. You hear them called fry. Fry is the term you'll usually hear for baby fish, especially freshwater fish. I think that may be partially specific for them, but fry is what you'll usually hear them called. And yeah, most fish go through metamorphosis. It's usually not as drastic as other organisms. It's usually, it looks like a little bitty version, but maybe it's missing its color and its proportions are off, kind of like us.
Yeah. It's a squishy version.
Yeah. But there are some that go through very distinct life phases. One of the most famous and most obvious are flatfish. Things like the flounder and stuff like that start life as a normal, quote unquote, as a bilaterally symmetrical fish with an eye on each side, swimming with the top on the top and the bottom on the bottom.
Right, torpedo shaped, roughly
like a fish.
like a fish.
And then as they develop, one of their eyes, and it's always the same eye, but I don't remember which one it is, but one of their eyes shifts over the skull to the other side, and then they slowly rotate until one side of the body becomes the bottom side now, and the other side becomes the top, the eye-facing side, and their mouth moves off to the side, and they become sideways fish to lay on the bottom and ambush.
So flounder in The Little Mermaid
Was a baby. When they go through puberty together, it's going to be real scary for Ariel. So like some fish go through really dramatic ones, and then some go through really complex metamorphosis life cycles, particularly ones that move habitats. Certain groups of fish start in fresh or salt water and then transition throughout their life.
River to ocean or ocean to river or something like that.
Absolutely. One of the most famous examples, and the one that probably most people are thinking of right now, are salmon.
That's what I was thinking.
Salmon. Everyone's favorite Digimon. Which are diadromus, which means they go from freshwater. They are born in freshwater and then transition to the sea. And to do that takes a form of metamorphosis, because you can't just throw a freshwater fish in the ocean because it'll die.
Right.
It will dehydrate because of the high levels of salt. So, when a baby salmon is born, it is a fry, it is a larva, and after months to years, as a fry, hiding in the rivers and feeding, it starts to develop bars and pigments and becomes a parr. P-A-R-R. And then they start moving downstream toward the ocean and undergo smoltification, which is parr to smolt.
Okay.
And so this is the point at which we are entering the true metamorphosis. And so this starts to get weird, because it can seem like fish go through multiple metamorphoses, and not everyone agrees that that's okay. There are some people that say, no, this is metamorphosis, this is puberty, or this is a difference, or this whole phase.
Yeah.
So here, this is one of those examples where, as it's going from parr to smolt, it starts to change to begin to be able to handle seawater conditions. And so this is going to include things like their metabolism adjusting, their osmology, the osmosis of their body is going to change to adjust for the salt water. Their skin gains more of a silver color to it. They start to use up their body fat. Their gas bladder increases, which is going to help them control their depth in the water. And their body shape becomes leaner and sleeker. This whole process, which can take a while they move from upriver to the sea, is considered one long metamorphosis.
Interesting.
But a weird part of it is, if they don't reach the seawater within that smolt window, they regress a little bit to continue surviving in the freshwater. The osmology reverts, and they redarken the skin, but they don't revert completely, so it's not a reversal of metamorphosis. So the article I read said. And then, when they're an adult and ready to spawn again to mate, they have to return to freshwater, and they go through yet another shift, where they go from a marine salmonoid to a gristle. They all have weird names. And these are, most of the changes that happen here are sex specific. The famous one is like males get those beaks to tear other males apart.
Right, to fight each other.
Mm-hmm. And after they mate, they die. So they're mostly not survival-based transitions. Part of the reason the adults die is because they've come back to freshwater and they can't handle it. Which is why this is sometimes seen as a form of puberty, not metamorphosis. An aggressive puberty. So this leads us into one of the topics of metamorphosis that is tricky, in that the definitions don't always cover all the bases. So one book I found, which was by Sarah McMenamin, goes over that there are a few different definitions for metamorphosis, especially when you get out of the invertebrates, the insects and crustaceans, and get to the vertebrates, the chordates, us with our spinal cords. One common one is that a metamorphosis is a transition that requires profound morphological and ecological differences between life stages and rapid transition between these stages, which makes sense. But this can be a very restrictive definition and can dismiss the more subtle changes that can happen in an animal's life that might take longer but still are distinct. The other popular one that they listed was that metamorphosis in chordates was a conserved period of post-embryonic remodeling. So after an embryo, after you're born, but your body then still gets remodeled. And that how extensive this is going to be regulated by hormones. So it kind of captures more of the range. The issue here is that it does not necessarily capture changes that may be controlled by other factors. This is focused actually on the thyroid hormones that cause changes, maybe not other hormones that could play roles. So Sarah put a definition in the book that says metamorphosis is an irreversible developmental physiological change that affects multiple traits during post-embryonic development. It is brought about by one or more endocrine mediators, so these are the hormones, and independent of sexual maturation or modifications or senescence, which is getting old.
Right.
So it is a change that happens after you're born that is majorly your morphology and physiology, so your shape in your organs, and is somehow controlled hormonally and doesn't have to do with becoming sexually mature or getting old.
Getting old in the sense of, like, your body wear and tear.
Yes, like becoming a senior of your group. So that's a pretty good definition, but it also drives the point home that the term metamorphosis seems to be more easily defined in different groups than others.
Right. As with so many categories that we try to slap onto natural things, nature doesn't actually work in categories.
Yes.
We're trying to draw hard lines where there are only blurry lines to be found.
And the variety is not quite as rich as insects, but the variety among chordates is still ridiculous. There's another great example of the shift from between fresh and saltwater, but it's starting in the ocean, which is European eels, which are born in sargassum, the floating seaweed, travel to a river, and then travel up the river where they spend most of their life, and then go back as adults out to the sargassum to breed. And they have multiple phases there as well, each with their own name. The babies are larvae. Then when they get to the river, they become glass eels, which are mostly see-through. Then they become yellow eels as they gain pigmentation, or elvers before that, and then yellow eels, then silver eels as the silvering begins, and that's when they are adults that go out to breed once more. And the silver eels actually lose part of their digestive tract because their point isn't to eat, it's to breed.
Right.
So this is a very insect thing, but in an eel.
Yeah, there are insects that'll do that, like mayflies very famously will be a larva for up to years.
Yep.
And then become an adult for a day or a similarly very short amount of time. And they don't even have mouth parts.
Yep.
Because that's not your job. Your job is not to eat.
Yes, don't get distracted.
Yeah, exactly.
Now, we can't mention metamorphosis and not mention frogs.
Of course.
So let's talk a little bit about amphibians. Amphibians do have a variety between frogs and newts and salamanders and caecilians, the legless group. They do have different trends, but for the most part, they all start larval, which is an aquatic form, basically always, and then transition to an adult form, which is sometimes aquatic, sometimes terrestrial, depends on which one you're talking about. Frogs definitely go through the most aggressive, where they start out with no legs, a tail, and as herbivores, and then develop 4 legs, no tail, and are carnivores. Whilst salamanders and newts mostly look like their adult form, but have external gills for underwater survival. Tadpoles, the larval frogs, do have gills, but they're in a gill pouch, so you don't see them. So they have very similar transitions. The frogs definitely have the most ridiculous, and it happens surprisingly fast for a lot of them. So frog tadpole is born, no legs and a tail, and then starts to develop the legs, but remains a tadpole for quite some time. So the front legs develop under the gills, and the back legs slowly develop after those, or more slowly. And then they have a stage of living off the vegetation in the water as a tadpole with little legs, and are herbivorous, and they have this scraping mouth part and a long spiral gut. That's why Poliwhirl has that spiral on its belly for digesting these plants. And then when they enter metamorphosis, they change aggressively and quickly, and they more develop the legs. They start to reabsorb the tail, reabsorb their mouth and gut, to then evolve a jaw that can now eat bigger prey. They also are going to be rewriting parts of their nervous system for this new stuff and grow a tongue. And the thing that's really crazy is that part can all happen in a day.
Wow.
And then they'll slowly reabsorb the tail over the next few days and be a frog.
Just that classic feature of metamorphosis of very rapid change.
Yes. So this really hits that notable change that you could go someplace on Friday to work and there'd be tadpoles, and then on Monday after your weekend there'd be frogs.
Yep.
There are some kind of exceptions here with like newts. I've seen things suggest they don't go through true metamorphosis because the young are typically predatory, just like the adults.
Right. So it's more like what we do, where you're just a tiny version of the adult.
But they still have gills, external gills that get reabsorbed when they transition into an adult form. So this is one of those where I feel the definition is clashing with what's happening, because they're not changing life behaviorally, but they definitely are transitioning from young to adult. So the definitions probably could use updating in a number of categories. But that gives you an idea of some of the varieties. There's lots we could have gone into, and I'm sure there's someone out there going like, no, this one has a really cool metamorphosis.
Send us on the social medias your favorite example of metamorphosis that we didn't mention.
You could do an episode on just the metamorphosis of each of these groups.
Oh, yeah. Well, there's so many different versions of it, so many different animals that do it, which makes one wonder what is the benefit? And I say that not only to segue into the next, because as I said, master of segues, but also because I'm wondering that.
Yeah.
Why would fish and frogs and a bunch of insects and crustaceans, possibly independently multiple times, have arrived at this very similar solution?
So, after a brief break, we'll look into what does metamorphosis look like in the past, like what fossil information do we have, and what is our understanding and our hypotheses about the origins of metamorphosis, and how and why it might have originated in all these groups.
I'm very excited, and quickly before I go, I looked it up on the internet, and aphids are hemipterans.
Hey!
I was right. Okay, to the break.
So now let's talk a little bit about the fossil record of larvae. But instead of going through just a list of larvae, which would be fairly plentiful just considering how long they've been around, but mostly just saying there was a larva this age in this place and it was of this thing.
Right. The take-home is there are fossil larvae.
Absolutely.
Just as there are fossil like we have fossil butterflies and we have fossil caterpillars.
But larvae do tend to be a little more sparse in the fossil record because they're squishy. The larvae are typically soft-bodied, squishy, and depending on which one you're looking at, your time frames also, which one is around for more or less time, can shift. So there aren't as many as the adults sometimes, but they do exist, and we have a pretty good amount of information on how far they go back.
Right. This is also generally true, to my knowledge, about things like frogs,
Mm-hmm.
where adult fossils are way more common than tadpole fossils, in part because adults have lots of bones
Yes.
that are doing... Like, some of the most iconic and identifiable frog bones are limb bones.
Yes.
And hip elements, which you won't find in tadpoles.
Because you aren't born with those.
Yeah.
So there is definitely a discrepancy, which affects our understanding. But we do have some. So wanted to go through a list of some of the interesting and kind of cool ones. One of them, just because of the age, was a larva of some crustacean cousin that is from 520 million years ago.
Wow.
So this is very early on.
Cambrian.
We're flirting just with the end of the Cambrian explosion with this. This is
Episode 9.
Yes. This was also notable in the discovery because there was one that was 3D preserved, so it gave them a lot of details about
cool.
its overall morphology and gave us some information to us about crustaceans.
So crustaceans were metamorphosing back to the Cambrian.
Absolutely. So that's a very ancestral feature for them. This was a known species named Liancoilia ilesabrosa and was weird. It was a member of a group known as the short great appendage arthropods.
Oh, I've heard of those.
Yeah.
What a weird name.
Right? They were named because of claw-like structures attached to their heads, which were likely used for feeding, maybe sensing their environment. These are very small fossils. They said fingernail clipping sized.
Wow.
From China, and because of its age, gives the first look at ancestral larval forms in arthropods. And it has some of the features that are expected, like it has a segmented body, which seemed to have added segments as it grew. It has the 2 large structures on the head, 4 pairs of branching legs, and then 3 additional pairs of legs that were less developed, and then a posterior tipped dagger-like appendage that had 2 paddle-like structures on either side. So it's weird. It's super weird. There's nothing I can really think of that looks like it nowadays. But, as you said, it does represent that larval stages go back to the base of the arthropod group.
Right. Pretty much at the Cambrian explosion.
Mm-hmm. Which makes it interesting to look at the history of arthropod larvae, because we do see that evolutionary history does not remain constant, because insects, the earliest insects, seem to have not had metamorphosis.
Right. So crustaceans had it separately from insects, one way or another.
Exactly. And I could not find any articles on that directly. So I don't have much more to say about that.
Interesting. Because the first insects, like true insects up on land, are Silurian Carboniferous.
Mm-hmm.
I'm sorry, Devonian Carboniferous, somewhere in that sort of 300 to 400 million year range. And yeah, they seem... So later than that crustacean, but seemingly ametabolous, not metamorphosing.
So we have information that it definitely seems ancestral to arthropods as a group, but has potentially been lost and regained. There are a lot of groups we find, though, that seem to have been doing it the same way for quite some time. Lacewings. Lacewings came up in a number of studies when I was doing research, and those are around today.
Mm-hmm. Neuroptera.
Yes, and the Neuroptera are famous sometimes more for their larvae, which include the antlions.
Oh, that's right.
So antlions are these little squatty larvae that dig holes and then catch insects that fall into their holes, and then they metamorphose into lacewings. And we find very similar antlion-like larvae throughout the fossil record. Some going back 100 million years.
So that general pattern of life stages that we see today has been in place for a very long time.
Absolutely. And some of them are still weird. There was one article described that had particularly long mouth parts. Like, they have these special mouth parts as larvae that both inject venom and digestive juices and then siphon out the goo inside the insect for them to feed upon. This one had these, like, long chopstick ones, and it also kind of almost had antennae, which they usually don't have. So there have been weird ones. I saw another picture in a paper of one that had a particularly long neck and then their little mouth part head on the end. So there's still been variety, but it seems like, yeah, that predatory feeding larva has been pretty consistent among lacewings for quite some time.
Interesting.
And then every now and then you get a larva that's just weird. So this was a larva from the Jurassic of some sort of fly that seems to be related to the snipe flies or water snipe flies, which are relatives of the horsefly. And both are biting flies. They feed on blood. And so that's why horseflies always get such a bad rep, is they have a really painful bite. This seems to be a cousin of that of some sort, but is real weird. So this larva, which has been named Kia jurassica, was worm-shaped and seems to be aquatic. It had a tiny head equipped with heavy and hardened mandibles, so mouth parts that were tough. Its thorax, so its midsection, it had a large ventral, so on the underside, sucker, which was armed with teeth around the edges. It had short legs with bunches of spines on its back and a tentacle-like extension near its rear end.
Oh!
Right? It just gets more
it gets worse.
Lovecraftian with each description. And what they think that this looks like is that it was a parasitic larva that would latch onto stuff like a leech and then feed off of blood, most likely.
Right, it was endoparasitic and just would attach itself to things and then presumably metamorphose later into something that didn't do that.
Or potentially did if it was cousins of a horsefly.
I guess that's true.
It just went from an ectoparasite, which is I latch onto the outside of your body and feed off of you.
Oh yeah, an ectoparasite.
Yep. And it was hematophagous, meaning it drank blood, which is unusual. That's not something we see in a lot of larvae today. And this whole body arrangement is particularly unusual. Like, they did not give any parallels in the...
So there's a variety of larval life stages throughout time, just like with anything else.
But by far, the coolest metamorphosis-related fossil finding by Thomas van de Kamp et al. And I think we might have mentioned this in a news.
I think if you're about to mention what I think you are, then I think you are right.
So not too long ago, some pupa were found and CT scanned. And what they found inside were the juveniles of parasitic wasps.
Right. So the pupae of some other insect that was metamorphosing and had been infiltrated by parasites.
Yes. So
by parasitoids.
Parasitoid wasps, which are still around today.
Yep.
Is a group of wasps, a very diverse group of wasps. It's actually
very diverse.
Insanely common among their group that lay their eggs in or on the body of another animal, but many of them target the larva or sometimes specifically pupa of other insects. And the egg then hatches and the young feeds off the other insect and then alien style bursts out of it to become an adult wasp. Sometimes it does that inside, but usually it comes out as a little larva and then metamorphoses itself.
I have to imagine that it must be very tempting to parasitize or parasitoidize a pupa.
Yes.
It's not fighting back. It's not doing anything. It's just sitting there. You stick your eggs in it and you go.
Which is why a lot of insects have hidden pupa. They're camouflaged and disguised to try to avoid that predation.
So not only has metamorphosis been around for a while, but things taking advantage of metamorphosis. Well, and just the idea of a creature that you put your larva to interrupt a stage of somebody else's metamorphosis, and then your larva metamorphoses.
Which means it's also vulnerable. There are wasps who have to worry about being attacked by other wasps' larvae. So it's vicious. And just for one last cool note on this, they found 4 different species of wasp, and they all were new, but 2 of them got put into a genus they named Xenomorphia.
Yes, that's right. We did talk about this in the news.
Which is the best name ever.
Well, because xenomorphs also metamorphose.
Yes. Yes, they do. They find shed skin in a number of the movies. Now, like I said, we could go on and on about cool examples of fossil larvae, but I want to make sure we have time to talk about what do we think /know/understand about the evolution of this weird process.
Right. How did this come to... How and why?
And the answer mostly is, we don't know. We don't fully know how it evolved because it's not super well understood in all groups today. So we still are teasing out exactly how it works with different organisms. And larvae don't always fossilize well. Right. Some better than others. And it's complex. It's different with each group. And because of all of that, we don't have really solid answers on how it evolved.
And in terms of the fossil record, even if we did have a good record of larval stages or pupal stages of various things, metamorphosis tends to happen very quickly.
Yes, it does.
Which means you're unlikely to capture it in the act.
Yeah, mid-chrysalis.
Right. You're very unlikely to see something mid-metamorphosis becoming fossilized. In much the same way that quick evolutionary transitions in the fossil record tend not to show up very clearly, because the fossil record is catching only a tiny portion of things.
Yeah, it's inconsistent and it's incomplete.
So it's rare, squishy things.
Yes.
So the fossil record is very limited in what it can tell us.
But we do have some clues, and we do have some pretty solid hypotheses about certain aspects of it. For instance, when it comes to arthropods, which is the group that makes up the phylum Arthropoda.
Right. Insect, spiders, crustaceans, etc.
According to analysis of massive data sets, one data set, this is all by Joanne Wolf, one data set was 217 preserved fossils of 96 extant taxa. And then there was another one where it was embryonic or post-embryonic fossils from 25 species throughout the stem group of crown arthropod lineages. So like big data sets all seem to come together to say that metamorphosis is ancestral to arthropods.
Okay, so the very earliest arthropods
were very likely going through metamorphosis. So the data seems to suggest that, no, it's something that some of the earliest Cambrian explosion animals were doing.
The first animals.
And then we do the general consensus on things like the amphibians is that it is an ancestral feature from the fish, which means that it is ancestral to chordates.
Right, which is interesting because we talked, back in episode 77, we talked a bunch about the tetrapod transition, and I've never seen anything discussed about early tetrapods, like Tiktaalik and such, being metamorphosing creatures.
Part of this lack of understanding can also be lack of research. A number of the articles I went through had lines that said it's not studied enough. That we need more research here because people are focusing on the adults, not the larvae. So there can be missing information. But as usual, insects have the bulk of that discussion, the bulk of that focus. So once again, earliest insects did not seem to go through metamorphosis. They seem to be ametabolous. Then somewhere around 300 million years ago, we start seeing ones that develop differently with a distinct juvenile state and a distinct adult state.
Right, and this is based not only on fossils that are similar to what we have today, but on genetic understanding of the relationships between the different groups of insects.
The ones that are and aren't going through metamorphosis today also give us information about these earlier groups.
Right, because as we discussed before, the metamorphosing insects are united ancestrally.
So one of the earlier proposals for why this evolved was in the 1600s by William Harvey, who was a physician, who proposed that insect larvae were free-living embryos.
Oh.
And that they had abandoned their, quote, imperfect eggs before they matured to feed outside. You know, these eggs are terrible. I need to go find food elsewhere.
Right. Insects aren't making good enough eggs.
Yes. and that the pupal stage was a second egg for the insect to be reborn as a new animal.
Huh.
So in this idea, they were distinct creatures. And there have been more recent hypotheses that kind of are along this line, but less judgmental on the insect.
Right.
There was one that noted the similarity between the larval forms of the complete metamorphosis insects and the embryo forms of the partial metamorphosis insects.
Oh.
So they noticed that a caterpillar is a lot like the embryo at certain stages of a grasshopper or dragonfly, and proposed that holometabolous insects evolved from the hemimetabolous insects, so complete evolved from partial, which makes sense, with the embryo developing to leave the egg more earlier in still a more embryo form.
You're born with a lot of traits held over from that embryonic state. We talked about this in the ontogeny episode, this idea of holding on to juvenile or early stage traits later into life.
And the cause that is proposed that would have led to this happening is if there was a reduction in the egg yolk. If there, for some reason, your nutrition was lowered inside the egg, it might prompt to continue feeding outside the egg.
Right. You're born earlier, and you're on your own. You got to get more nutrition.
Yes. And that the pupa phase was basically as the larval and adult became more distinct from one another, that nymph phase just got turned into a pupal phase. Because now there was more distinction that needed to happen during metamorphosis, or needed to change to catch up. That's definitely a little closer to more acceptable than the other one.
A more modern understanding.
More modern understanding. But that's not to say all of our modern understandings are great. I found an article in 2009 that suggested that butterfly metamorphosis resulted from the ancient and accidental mating between two different species, one that wriggled on the ground and one that flitted through the air. I'm quoting. And was very quickly and within the same journal debunked quite aggressively. So we'll link to an article about that.
Right.
But there are still misconceptions that are getting thrown out there. One of the strongest and most supported of the hypothesis of how complete metamorphosis evolved in insects has been championed by Lind Ridderford and James Truman, who popped up all over the place when I was doing research.
The big names.
They seem to be some of the champions of this concept and topic. And they are also saying that yes, complete metamorphosis evolved from partial, but in slightly different ways than has been proposed and for more clear reasons. What this really hinges on is that in many arthropods, there is a pre-larval stage that is sometimes almost unnoticeable or doesn't last very long. And so this is a stage where right after hatching, sometimes pre-hatching in certain groups, that has unique features from the larva. It's obvious in a lot of aquatic crustaceans that start out as plankton, but it's present even in the partial metamorphosing insects, but typically only within the egg. And so there is a stage they go through before becoming a nymph that may only last a few days or just a few minutes.
Wow. Very
brief phase that is actually fairly similar to a more caterpillar-like larva.
Okay, so even the partial metamorphosing insects have this intermediate, I'm about to be a larva, I'm about to be a nymph section that looks like the complete metamorphosing larval stage.
Yes. They've named it the pro-nymph.
Okay.
So this pro-nymph, which is very wriggly, very wormy, and is typically inside the egg. For some, it lasts for a very short time outside the egg. And that's the one where it may only be they've hatched and then their immediate next shed is to then come out of that form. But this pronymphal phase is as they're developing the egg and feeding off the yolk. They suggest that this phase persisted outside the egg for some reason. And they give some suggestions as to what steps might have happened to cause that to happen. And it's not too far off from the previous explanations. So if for some reason there was a mutation and the nymph failed to absorb all of its yolk, so the yolk didn't run out, but it did not absorb it like it normally would, it would be benefited if it could eat it while still in the egg. If for some reason they weren't absorbing their yolks, but some were able to start nomming on the yolk in the egg, they would survive and be healthy.
Right. It's a measure to protect against something going wrong
Yes.
in the egg. Say, okay, even if something goes wrong in the egg, you can eat the yolk, so we're increasing our survival chances.
So if at some point a mutation caused a portion of larvae to stop successfully absorbing their yolks, most of those wouldn't survive until another mutation allowed some of them to start eating the yolk, and then they would now persist with this advantage. Then, if yet another mutation caused them to hatch slightly early, but still retaining that ability to eat, now they can continue to eat out in the world. And then all that needs to happen is for that time that they stay this pro-nymph to be lengthened and lengthened.
And it would make sense to me that if that's the first stage outside the egg, once you have that, which it sounds like some insects already do.
Some of them can spend a few days as a pro-nymph before becoming a nymph.
Then it's just extending that period, which seems like a pretty, as changes go, easy change to imagine happening.
That's pretty reasonable. And it makes sense on how there could be benefits. Is if you're doing well, if you grow really fat eating as a pro-nymph outside the egg, that's a good reason to stay a pro-nymph.
And we've talked as I said in the ontogeny episode, we talked about how there are animals today that will do that sort of thing, like salamanders that will start it out as you're an aquatic larva, you become terrestrial, but evolutionarily over time it became beneficial for some of you to just not leave the water.
Yeah.
So you retain those aquatic juvenile traits into adulthood, and now this is a benefit that allows you to survive in a different circumstance.
And a cool part of this is it's supported by the hormones that we see in the insects. So insect metamorphosis is also controlled by hormones, but theirs are different than ours. And there are different groups of them. One is known as the juvenile hormone, which suppresses the development of adult features in larvae. They're not as present in the nymph phase of partial metamorphosis insects, but caterpillars are full of them, and so are pronymphs. So we see a similar pattern in the hormones that are passing through and being active in a caterpillar and a pronymph. So there seems to be a lot of support. There's also a lot more to the hormones that gets way too much into biochemistry. So I can't explain it, but there's more support than just that.
Right.
And so there seems to be a strong case for a caterpillar is just a very early, it's not an external embryo, but it's a preemie insect, if you were asking the grasshopper. And so we have a potentially solid hypothesis on insects. When it comes to us chordates, we don't have a solid answer for how it evolved per se, but we do have an answer that it does seem that it evolved once. Because it is, for all chordates, it seems to be controlled by thyroid hormones. That seems to be the main key, those hormones to trigger metamorphosis. It's true in frogs, it's true in many fish, and it has now been found to be true in lancelets, the little filter-feeding potential cousins of some of the earliest chordates.
Right.
These are often considered to be the most basal of chordate, spinal corded animals. And they look kind of fishy, but they've got a little filter-feeding mouth, and they stick in the sand, and they very heavily resemble Pupae, which dates back 530 million years ago, and is one of the earliest ancestors to chordata.
So that would suggest that metamorphosis is ancestral to chordates, to vertebrate ancestors, in a very similar way as it is with arthropods.
Which did lead one article to say that potentially those wormy things in the Ediacaran could have been larval things. That is part of that the larval stages might date back before the Cambrian explosion. Yeah. We just don't have good fossil record.
Which brings up Ediacaran, by the way, episode 31.
Mm-hmm.
But this brings up a fascinating complication when looking at the fossil record, which is that it can be difficult to know which larvae go with which adult stage of a thing.
Much like ichnofossils with trace fossils.
Right.
If your baby, by definition, does not show the features of the adult, then unless you find them associated, it might be difficult to correctly identify them.
Yeah. How would you know, if that, without watching the life cycle, that this particular caterpillar becomes this particular butterfly?
So this leads us to the why. Why do all these animals metamorphose?
Why have you... And by the way, here's a note on terminology for all of our listeners who are listening. If you're wondering, we have kind of bounced back and forth between saying metamorphose and metamorphosize.
Yeah.
Internet tells me both are correct.
Yeah.
So there you go.
I like metamorphose.
I like metamorphose.
That's always been my preferred. So there are a few ideas as to why. And one of the biggest ones is that, like you were talking about in our news with the tyrannosaurids having their own areas, this allows for niche partitioning within a single species.
Right. We've talked about this with non-metamorphosing animals.
Now, my baby is not eating my food. It's eating gross leaves while I go get nectar from the flowers.
Right. A cultured...
From a more civilized
type of food. From a more civilized age.
And so what this allows is now your young and yourselves, you know, the young and the adults can occupy the same space, the same environment in greater numbers of each because they're now eating different things.
Right. Which would make a lot of sense for animals like insects or fish whose reproductive strategy is to fill the environment with as many of your young as you possibly can.
Absolutely. So now you're avoiding conflict. You're also distinguishing tasks. So kind of like eusocial insects where like there's the guard ants and the worker ants. It's more efficient to have one person do one job than to have everyone do all the jobs. Now, as a baby, your only job is to eat and get fat. As an adult, your only job, potentially, is to mate.
Right.
So now you are able to specialize. What's the most efficient way to eat and get fat? Look like Jabba the Hutt. You need to be a wriggly worm that can put on fat with elastic skin, and you're specialized for eating leaves. As an adult, you need to get around and disperse, so here's some wings. You don't need wings as a caterpillar because all the leaves are right here. So now you can specialize. And you can utilize different parts of the environment. If I'm a beetle grub, I can bore into a tree, which the beetle can't do. But now I can eat this stuff, which the beetle wouldn't have been able to take advantage of. Now both the species have taken advantage of both environments by being different shapes.
And I think it's interesting that we have animals today that do that without metamorphosis.
Yes.
Metamorphosis, by the in that the go-to example for us has always been alligators, which as babies live a different way, eat different food, and then as adults are doing something totally different. And in their case, one of the reasons that it's so important and that they get away with it is because the size difference between a baby and an adult is ridiculous, but it's not difficult to imagine that sort of partitioning in a non-metamorphosizing animal where you've got, all right, the little ones live in the shallow end of the pond and they eat bugs, and the big ones live on the shoreline and the deeper end and they eat deer, and that just becoming more exaggerated over time and your transition becoming more concentrated.
This is the logical next step to that sort. You know, if you were designing things, at some point someone would go, well, if all they're doing is eating bugs in the shallow, why don't we just make them to eat bugs? Like, that's way more efficient than using the same kind of mouth for both.
Right. Why don't we, if the little ones can't even eat turtles, why don't we not even give them crushing teeth until they are adults, which is what alligators do.
Yep. And so these all are benefits that we can see how they'd help. And there is research backing up that, yes, it was beneficial in this way. There was research that looked at insects that partake in metamorphosis, looking at a database of 1,500 fossil families.
Wow.
And what it found is that insects that undergo metamorphosis display a greater turnover rate of species and therefore have a higher rate of diversification. And so when we see metamorphosis enter in to the insect toolkit and we look at the groups that have been doing it, they have higher diversity and therefore also seem to have a lower extinction rate. So it seems to be a direct correlation between the two. And one of the reasons they also point out is it could also shorten developmental times because you're specifying. And so it speeds up the cycle and decreases the time that you're getting ready to have babies again. So there's direct evidence that shows, no, it has been particularly beneficial to the groups that use it. And the last thing that is a potentially interesting aspect of metamorphosis is that if your larva and adult are so distinctly different, it means that potentially natural selection is affecting each differently.
I was hoping you would bring this up, because this is the most fascinating part to me. It's like, caterpillars and butterflies will evolve for different reasons.
And the research seems to suggest that, yes, that is the case. That natural selection is putting different pressures on adult and young. And it was found in the European eel that we mentioned before that the genomes seem to show that, the larvae are under different selection pressures than the adult, which therefore means that you're getting kind of like two goes and each one is becoming more and more specialized for their roles in your life cycle, regardless of what the other one's doing. And that can be a huge boon to specializing you to environments.
And that, I think, is one of the most fascinating parts of metamorphosis, because the potential side effects of that are so interesting.
Mm-hmm.
Because you could have a circumstance, thinking about this in terms of the fossil record, where, like, the larvae are under strong selection to change rapidly, but your adults are doing just fine.
Yeah.
So you could feasibly have a larval form change dramatically, but while still metamorphosing into a fairly similar conserved adult version.
Yeah. And they term this opposing selection pressures versus complementary.
Right, which is the other cool thing, is that you can imagine that they could, if they're evolving for different reasons, they could evolve stuff that's not good for the other one. Like, if your larva it becomes beneficial for your larva to find food in a colder habitat that the adult form can't survive in, well, then what do you do?
Yeah. So you can get some weird stuff. And we're still understanding it. Like,
yeah, it wouldn't surprise me that if we just don't really understand that very well. Because, again, not a ton of fossil evidence for that kind of thing. That sort of thing is more difficult to study using just living species.
Yeah. We need another one of those long-term research projects. And with that, I think we're going to wrap up our discussion of metamorphosis.
There's a lot there.
If there's something we missed, let us know. If you want to hear us talk about it more, let us know. And if you have a particularly cool or favorite example of metamorphosis, share it. We'd love to hear what everyone thinks is the coolest example of this weird life cycle.
And we'll have some cool examples, pictures, links, as always, in the blog post.
Yep. But before we end the episode, before our outro music plays, we have a patron question.
Oh, that's right. Some of our patrons at a certain level get to ask us questions for us to answer on the podcast.
They do indeed. And this one's from Philip, who asks, or who says, in our Dragon Con panel, it's mentioned that there was medullary bone found in Sue, the T-Rex. Is this true? Can't seem to find any publications or mentions of this.
Right, so if you listen to our Dragon Con panel, which we released recently, everybody go listen to it. We had a big Q&A panel at Dragon Con where people could ask us paleo questions, and the subject of medullary bone came up, which is a type of bone that we see in birds today that are getting ready to lay eggs, and has been observed in some dinosaurs that presumably were also getting ready to lay eggs.
Which is cool.
Which is very cool because it's a unique type of bone. It tells you about a life stage, a process that your animal was going through, but also is one of the very few surefire ways to identify a female.
Yes.
Because presumably males aren't developing medullary bone. And in that discussion, it came up that Sue, the famous T-Rex, might have been one of the specimens that this was discovered in. And I think that was an error on the part of us panelists.
Yeah.
Because I don't think that's true. I've looked into it, and I know that there have been 1 or 2 tyrannosaur specimens that have had medullary bone discovered, identified inside of bone. I don't believe Sue was one of them. I've not seen anything brought up about that. There has been medullary bone identified in T-Rex.
Yeah, so, like, it's happened.
Right. I don't, to my knowledge...
Just with less famous individuals.
Yeah, this is the ones that didn't have big, cool names. But that is a good question.
Absolutely. So thank you for the question, Philip.
And thanks for listening to our Dragon Con panel.
Yeah.
Fun fact, I also believe that there has been medullary bone discovered in at least one pterosaur specimen.
That's really cool.
Which just... Oh, boy, that
that's
just makes me so happy.
That's awesome.
So, yeah. Also not named Sue.
We don't know. We didn't know them.
That's not... for anyone who's unfamiliar with Sue, the famously, very famous specimen of T-Rex discovered in South Dakota, has a really stellar Twitter account.
It's pretty great.
Check it out.
And with that, we can now wrap up our question and wrap up the episode. As you said, if there's any aspect of anything we mentioned that you want to hear more of or that you have questions on, send them to us. If you want us to answer them on the podcast, look at our Patreon and we'll be happy to do that. We'll put lots of cool links and pictures in the blog post, so check that out. You can contact us for any of these reasons and others through all of our social medias and emails and all that stuff.
Including Instagram.
Including Instagram now. Send all of your questions specifically there so that we'll have to go use it.
Yes, we'll have to learn.
We release episodes every fortnight.
So stay tuned.
And thanks again for listening, everyone.
We'll see you next time. Who knows what will be by then?
It will be beautiful butterflies.
Beautiful butterflies.
From up here, you all look like ants.
Thanks for listening to the Common Descent Podcast. You can follow us on Facebook, Twitter, YouTube, and check our WordPress blog for pictures and links after each episode. Huge thanks to our patrons whose support helps keep this podcast running and who get access to bonus goodies on Patreon. The song you're hearing is called On the Origin of Species by Protodome, which we found at ocremix.org. Thanks again for listening. We hope you'll join us next time.